Now, let's look at rubber elasticity from a thermodynamic perspective. So, as usual, let's go ahead and look at our polymer network starting from Gibbs. So, if we differentiate Gibbs, again, you could go back to kind of our refresher on thermodynamics, but we get this following expression here. So, we can now look at, again, our usual system, but we're adding essentially our work term or, extension in our kind of U. So, we have this expression here, and we have our force per unit chain. So we can see that basically our force is essentially going to be equal to dG/dL at constant temperature and pressure. Why? Because then all these rest of these values are nothing. So that's our expression. So we can now actually basically take the derivative and kind of rewrite our function as a function of this. So my force now, if I do dG/dL to each of these variables at constant temperature and pressure, I could start to kind of write some of these values. So you can see here that actually, let's go ahead and put it up. So if I take this expression and I plug it into here, my F is going to be equal to basically dH/dL, constant temperature and pressure, minus T ds dL, constant temperature and pressure. I could take the derivative, the differential of dt ds, but then again, that's going to be equal to 0 because constant temperature. So we see this expression here. But remember our physical interpretation. And we said that basically the force association is going to be, one of the assumptions that we made, or that we kind of implicitly made, is that we're going to assume that as we pull our material, we're not going to expose any new binding sites. So you see here that, again, we have this kind of enthalpy, term. So we're going to assume that there's no kind of sites opened up, and that there's going to be no conformational changes that changes essentially the reactivity of our polymer. So we're going to assume that this is essentially going to be 0. So there's not going to be any change in enthalpy as we increase our force. Now, for certain polymers, that's definitely not true. So bottom limit factor, for sure, 100% not true. But for many polymers, this holds true. And we're left with the following expression. And this is really, really, really important. Again, we're working with ideal rubbers. That's another assumption that we're making in here. But here, we see that our force, we have a restoring force. And it is completely entropy driven. So it's not very dissimilar to our kind of crystalline metals and ceramic materials, or basically glassy amorphous materials as well. So we see here that the restoring force, we have an entropic spring restoring force that's going on here. So we assume that there's no change in enthalpy when the rubber is stretched, but part of that is because of the fixed volume assumption. But anyways, volume's not changing, so net number of reactions constant, blah 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 blah. Again, it's the same thing we've been kind of talking about. And this is very unique in terms of, again, for polymers. So it couldn't work for metals because of bond stretching, and actually it still dominates even regardless. But we know, for example, that when I stretch my material, I'm reducing. So as my length increases, my number of microstates, my entropy decreases. So ds/dl will change, and that is going to be actually negative. So you're going to see here, again, the derivative, we have to calculate the entropy anyways, but we're going to see that the change in entropy is going to decrease as I increase my length. And so I'm going to get this restoring force, this positive restoring force that wants me to kind of, basically, it wants the material to kind of go back. So as I take my, my polymer, and as I stretch it like this, there's going to be a force that wants to restore and oppose that force. So and it kind of makes intuitive sense. So that's kind of the cool part. So next time we're going to actually look and see, because again, we know that force is T ds/dl. So we're going to actually have to calculate this. And we're getting to a nice, fun derivation next time. So see you in the next video. Thanks.